We're going to run through how to implement model predictive control on a nonlinear reactor. So this is our reactor right here. We can have our cooling temperature right here. This is our jacket temperature in our reactor, around our reactor, and we can adjust that up or down in order to be able to maintain a temperature. So the temperature is going to be our controlled variable, and our manipulated variable, the one that we can adjust or the controller can adjust, is going to be the cooling temperature. Okay, so let's get to it. We've got a, if you go to the course website, okay, go take a course, and then this is our dynamic optimization, and then scroll down. This is going to be under nonlinear control. Go ahead and select that. You'll see this model predictive controller. Okay, a little bit of information on this application. There's our step test with a doublet. We have our CSTR model implemented here in Python, and this is one that we're going to try to control. So this is a nonlinear common benchmark problem used in many publications, and there are the differential equations, a species balance, and an energy balance. Okay, we're going to use ODEInt just to have our simulator, but we want to implement model predictive control on top of this. Okay, and we have this simulation loop right here. This is going to simulate the CSTR, and we're going to run through all of these time steps until we get to the end, and then compare, how we did matching our set point for our reactor temperature. This is just some plotting down below. So what I'm going to do is, first of all, just go ahead and start here. If you want to select Get Code, I've already done that and then just saved it into a file on my desktop. I'm going to use Python 2.7, but you can also use 3+ for this. If you just run this, this is going to be our very first one. We're just going to run it, and this is our doublet test. Now what we would do is we'd do this doublet test, fit some first order plus dead time models or a linear dynamic model, and be able to obtain that. I'm just for the purposes of this exercise, I'm going to go ahead and assume we already have done that, and we just want to implement our controller. Okay, so the first thing that we're going to do is let's go ahead and just implement, let's go ahead and take out the doublet test first of all from this, and I'm going to do the time intervals. I'm going to change that first of all just for our controller cycle time. I'm going to go up to let's see, 5 minutes there, and let's just do 0.05 intervals. I'm going to use the A range. So it's going to go between 0 and 5 with 0.05 minute time intervals. Okay, here are my cooling temperatures right here. I can just take out this doublet test because I don't need it anymore. This is going to come from my controller now. So here's where I simulate the CSTR right here. I'm going to insert my controller right here. Okay, so this is going to be my controller, and I'm going to have a new temperature. Okay, so this is going to be my new cooling temperature, I+1. There's my new cooling temperature. I'll just name this differently so it's a little easier to read. I'll do TC. Okay, am I already using that one? No, I'm not. Okay, equals MPC as a function of the measured temperature. So the measured temperature from the very last cycle was Ti+1, so I can use Ti there. Okay, there's my measured temperature. I'm going to create this new function that's going to have as input my measured temperature of my reactor, and then it's going to output what is my optimal cooling temperature. There's my MPC controller right there. Let's go ahead and define this. This is my MPC controller, so I'm just going to build it as if I already have the MPC controller initialized. I don't yet. We'll do that next. So I have the temperature as the input, and then I'm going to insert that as a measurement into my application, and I'm just going to call that okay, there's my temperature, and I'm going to use the APMonitor solver to do this. I'll solve it and then get the next, I'll get the cooling temperature from the application. So we just have to remember those variables names. I'll get the new value from that. Okay, this is my MPC controller right here. Once it's initialized and set up in solving, it's really only 3 lines. I insert the measurement into the application, I solve it, and then I retrieve the new cooling temperature. We need to do something first. We need to initialize the MPC controller. Okay, MPC, I guess controller is kind of redundant there. Model predictive controller. So I'm just going to say initialize MPC. And let's do MPC init. Okay, this one's going to be just a little bit more involved. We're going to be setting up our model and our time steps and all that. Okay, so first of all, we just want to create a new model file. And so I'm going to open up a new file, and this one's going, I'll just call it model.apm. Not very creative there, but let's go ahead and do write, and we need a bunch of these, so let's go ahead and just write lines with a new line character there on down. Go and copy it a bunch of times. That's about how many I'll need, and then I'll close it. Okay, if we run out, we can always copy that one, make some more. Okay, let's go ahead and write our model file now. I'm going to go ahead and just do constants, and just trust me on these. This is my steady state temperature for my jacket. Okay, this just came from the doublet test. Here's my steady state from the reactor. Okay, and let me get a couple parameters as well. Here's my model. My K value, this is my gain. Let me just put 1.3 in there, and a time constant. I'm going to do about 0.9 minutes. Okay, this is from fitting a linear model to the data. Variables. Okay, variables. I'm going to say that T is one of my variables. I'm going to initialize it to the steady state value that I had, and then let's go ahead and do an equation. Okay, equations, and here this one is going to be the first order linear model that we identified from a prior exercise. Okay, let me go ahead and just write this. This $sign right here, this means differential, so it's d temperature, d time. Okay, and then we have plus K times TC minus TC steady state. Okay, there we go. We are done with our model. We don't need the rest of these. Go and delete those. Okay, there's our model. We've written our model. Let's go ahead and write, in addition, let's go ahead and write our prediction horizon. Okay, I'm just going to go and create a lin space between 0 and 1 and 21 time intervals, so 0.05 for each one, for 1 minute out into the future. And I'm going to open up another file here. And this one I'm going to call data.csv. Okay, it's just a data file, text file, and comma separated values. We only have one column though for this one, so you're really not even going to see any commas in there. Okay, and I'm going to write a header, and then let's go ahead and do a for loop for ti and t. Okay, so I'm going to visit all of those time points, and I want to write each of those time points that I just created. And let's see, I'm going to do a new line, put my number in there, and do format of my TI. Okay, so this is just going to write that line, those times that I just created in the T vector with the lin space, and then let's close it. Okay, so there is my data file. That defines my time points and my horizon, and I could put feed forward variables in there as well. if I had another column. Now let's go ahead and just go through. I'm going to do a server S and A. Those are going to be my server and my application name. I'm going to go all the way to the top and just define those right now. Let's see. We're going to need to from APM import all, and then my server. Just go ahead and use the publicly available server. You can also download a copy of the server if you want to use it on your own computer without an internet connection. And then application name, I'll just call this MPC. Okay, now I'm going to go down again. And okay, so there's my server and my application name. First thing that I want to do is just if there's anything there from the prior time, just go ahead and clear it. And let's go ahead and load our model file that we created right above. Okay, so model.apm, we just created that right above here. And then we also want to do a CSV load. Okay, and this one's called data.csv. So we loaded our model and our data file. And now we need to create some options. The very first thing we want to do is just classify some of our variables. Our MV is going to be cooling temperature, and the CV is going to be the temperature. Okay, the temperature right there. And let's see, now we need to have some options. Okay, so now this one is whether or not we want to use the measurement for TC. I'm going to turn that off, the status, F status off. I don't want to use the measurement of TC. I'm going to be driving it, but I do want the status. This is whether it becomes a degree of freedom as a manipulated variable, and whether it's going to be using TC to control the reactor. We want that on. Okay, let's go down a little bit. Well, let's go ahead and copy these same two for temperature as well. This is the temperature inside a reactor. Now in this case, we do want to use a measurement. We have a measurement and we want to use that. Okay, you saw that right here. There's our measurement we want to use, and we want the status to be on. We'll include it in our objective function. Okay, let's come up with a couple more of these as well. Okay, so let's go ahead and define our set point. This is going to be a set point range. I'm going to create it a set point high. This is our upper limit for our set point, and our lower limit for our set point. 290. I'll just put a 0.1 plus or minus 0.1 there. Okay, and then I'm going to also define a time constant, and I'll show this to you as we run it. Just what that means. I'm going to use 0.1, so 0.1 minutes. I want to get 63% of the way there in 0.1 minutes. It's just a first order time constant of how fast I want the reference trajectory for my controlled variable. And then the other thing I'm going to do is just, this is an option, trajectory initialization. It just means use a reference trajectory. That one is for don't change the initial point based on the current measure value. Two is recenter it always where you're measured, and then 0 would be just a dead band with no reference trajectory. Okay, let's go on to a couple additional options, and I'll explain those. If you didn't understand that last part, I'll explain those just a little bit more as we run it. And I open up a web viewer and can show it to you graphically. And I'm also going to change the web plot frequency. We want to update those every second. So that's just by default every minute it'll update those, but in this application we just want to, we want to update it more frequently. I always feel like I have to return something. Okay, successfully initialize. I'll return a message. Okay, so there is our initialization. We need to make sure we call it MPC init. There it is. We've initialized our MPC. Okay, so let's come on down here a little bit more. Okay, so we went ahead and have our MPC controller. It does three things. It inserts the measurement, it solves it, and then it gets the new value back. We also went through the initialization. We defined our model. There's our differential equation model. You can put nonlinear equations in there as well, differential algebraic equations. There's our time horizon that we want. These are just some commands to load the model and data, classify some of the variables, set some options, and we're ready to go. Okay, so now we have CSTR, we have our MPC controller, and let's just do let's do one other thing here. In this, we'll go ahead and we have TC defined, but we need to relate that to the U I plus 1. We just renamed it there, T equals TC, just so it'll use it down here. When it integrates the system, it'll use our manipulated variable. Okay, and then the other thing I'll do is, if I equals 5, let's go ahead and open up a web viewer. That'll be nice just to be able to see what's going on, and if it's, you know, the 50th interval here, we're gonna I equals 49, we're gonna change the set point. So we had these set points right up here. Let's go ahead and just copy those, put them down here, and then we'll change it just so we can see something different happen. I'm going to change it up to 320 to 3.1 to 319.9. So it's going to change the set point just so we can see it tracking the set point as it goes. I think everything else should be the same. Okay. I think I want the set point on there too. Well, I'll add that later maybe. Okay, let's go ahead and run this and see where our first error is. Okay, I forgot the colon there. Okay, let me see. I probably forgot it on the other one too. Oh, no, I got it. Okay, let's run it again, see where our next error is. Save it. No module named APM. Okay, so if you don't have the APM module, okay, we tried to import it right here. Just come to APMonitor Python. Okay, and you can get it from here if you want. You can also get it from GitHub. You know, let's go to GitHub and just grab that. Okay, I'm going to go down to APM Python, and it's right here. Okay, so what you can do is just go raw, copy it out. If you want, I'm going to Control A, Control C, and then just make, what did I just do there? Right click, and then go new, and text document, and I'll just name this apm.py. Change it, okay, yes. And I'll just paste that I just copied. Okay, so this is the APMonitor module that you can just load. And I'll save it. Yes, okay, so it's there, and now I can import it. You just need that file. You can get it from GitHub, or you can get it, you can download it. Go back to the Google search. I'll just show you another way to get it as well. If you want to just get it, let's see, you can pip install it as well. Just have to, if you pip install it as APMonitor, you just have to do from APMonitor.apm import star. Okay, just a little bit different way to import it if you do pip install. Okay, or you can just download it here in a zip file. All right, so let's go ahead and run it again, see where our next error is. Okay, global F. Okay, so let's see. Let's go down to our file. I think I messed that up. Okay, I'm just going to change this to, instead of FID, I'll change it to F. Wow, I did it FID correctly there. Okay, so I'll change that just for writing the files. Okay, let's stop this. Okay, we have an error. Let's go back here. Okay, invalid element TC. You can see this. It puts a question mark right underneath the place where it said, I don't understand this. You need to fix that in your model. And it looks like I forgot to define my T sub C. This is my cooling jacket temperature. Oops, I did delete there. Okay, and I'll say that that's 300, and that'll be TC. So I just didn't have it defined, and it said, whoa, I have an error down here in this equation, so I don't know what that is right there. Okay, let's go ahead and go again. I'm going to run module. Ooh, I saw an error there, I thought. I'm not quite sure. Okay, so, whoa, that doesn't look good. Let me go back here, and I think I know what it was. I forgot to bound my TC. That needs to be less than 350 and greater than 250. So I need to put in some bounds there on my TC value. That was given in the problem statement, and it went to really low values really quickly if I didn't put that in there. So let's run it one more time. Okay, so it's going to go through all of these different cycles. And again, I got that red message there. I need to go back and see what that is. I'm going to come here and you can select the different plots. I'm going to select the temperature. Okay, looks like I hadn't given a, I gave the wrong initial value. Okay, so let's close this. Okay, so let's fix a couple things here. I have temperature steady state. Okay, it's 324. That looks correct. Okay, and let's go down here. TR init. Okay. Okay, so I'm just gonna do a little bit of tuning here. See if I can fix this up, because I want to show you guys how this thing runs, and then hopefully let you turn it over to you, see if you can improve it further if you'd like to. And okay, I'm going to change this to 0. I'm just going to put a pure deadband there. That's often the easiest one to do. And then in that case, I don't need the tau value, because it's just going to say try to reach that set point high and low as fast as you can. Okay, and I'm going to also go back on this console and see what that red, I saw a little bit of red flash up, like on the first or second. There it is. Okay, I'm going to stop. Okay, and then let's go back up. So often when you're running these applications, you just have to debug it a little bit. So illegal input detected from ODE pack. Oh, okay, that was an ODE int error. I wonder what that was. Okay, so there's some error there from the ODE integrator that illegal input detected, internal error, and you know what? I don't know what that is right now. I could put some print statements in there and figure that out, but let's just go ahead and see how this thing is running. Okay, and whether it's trying to meet that set point. Okay, so it is. Here's the plot right here. I just stopped it before it got too much further. I'm going to go ahead and maximize this. So here's our measured value right here, and then it started changing. Okay, you can see the measurement. You know, it's going to come down. There's, for some reason, it looks like, you know, this is maybe where my red error occurred. I don't know. But you know, you can see this come down to the set point, and then it's going to track along it. The model was predicting here, okay, it lowered the T sub C value, and then it got down. Okay, so there's some mismatch between the model and the measured value, but it handles that okay. Okay, it implements this this bias here. Okay, so if it sees a difference between the two, it shifts up this prediction right here, and then this comes down. Okay, let me come back to, let me just look a little bit more at my CSTR integrator, see if I can see anything that looks suspicious here. Okay, no, everything looks okay here. I don't see any problems with that. I'm just putting in the new initial conditions. I'm only simulating for, every time I go through, I'm only simulating for this amount of time right here. And it may have been, I may have redefined my time. Okay, let me just change this. TCSV. Okay. And I'm just going to look at a couple of other things here. Just make sure I didn't mess something else up. Okay, I think everything looks okay. Let's let this thing run for just a little bit and we'll just see how we did with our controller. Okay, so it's going to run and it's going to open this up, and let's just see our controller running now. And you can see it tracking here. Okay, so it's going to be going down, and then it goes over. And I'm going to go back to config and see if I got my web plot. My web plot frequency is 1 there, but for some reason it isn't updating. Okay. Okay, so in this case, there's just 1 or 2 little things that I'm still not happy about. So let me just show you, I'm going to show you this data file, and then I'm going to show you where you can go and just download the solution if you want to work with it. There are times right there for our time horizon. That's the one that we wrote. And then our model.apm file. Here's our model file that we wrote in our Python script as well. And what I'm going to do is just go ahead and show you, okay, so you can come down here and download this right here. Here is our model predictive control solution, and go ahead and save it. I went through all the major steps with you. There's just maybe a slight difference here. And if you go into MPC 3, okay, this 3 MPC, go ahead and edit this. And go ahead and run it. Alright, so now it's going to run, and let's see if it brings up this. Okay, so this is the one I developed previously, and if you want to just use this one, you can. You can see the controller tracking there. You can see it trying to track that black line, the track high and the track low. There's actually a little bit of a gap there. And if you ever get this message, just refresh your page and select it again. And there you can see the set point just happened. And there it's tracking to 320. Okay, I'm going to refresh the page. Let's just select and set the cooling temperature. And so you can see what the manipulated variable was doing over that time horizon. Okay, refresh again. I'm going to go back to temperature. And you can see it did a pretty good job of tracking the requested set points. Now in this one I had the reactor set point and the temperature built in there. So this is a little bit more of a complete plot than what I just showed you. So if you want to go and just download this from the website, you can see the CSTR linear model predictive controller solution in Python. And so just for comparison, I also threw in the PID controller. So if you'd like to compare that with a proportional integral derivative controller, you could run that one and see the performance. This is a tuned PID controller. Now MPC and PID, just for single input, single output, there's not going to be a lot of difference there. Okay, and but for more complicated systems, then you're often going to see a lot of difference, because model predictive control can take advantage of the multivariate relationships between variables and also drive to constraints, versus using something like anti-reset windup. Okay, so this is the model predictive control solution. And you can see it does a good job of following the set point as well. You can see that. Okay, and I'm going to go ahead and close this out. The one final thing that I included there, here's a linear identification. If you run the simulate first, so this is how you can obtain a model. Kind of glossed over that right at the beginning. You might do a doublet test, a step test on your system. Come up with the data file. Okay, there's my data, my time, my cooling temperature, and my outlet reactor temperature. And then here is a script that will do an output error model, a time series model will fit that. This is with the IPOP solver. And then you can see the regression there, the fit to that data. Okay, I'm going to go ahead and close that. And what it did is it wrote your APM file for you for your linear model predictive controller. That's in discrete time series form. Okay, so that concludes this this tutorial on model predictive control. What we did is we took our CSTR, we implemented a model that describes the relationship between the cooling temperature and the reactor temperature, and then we defined the model and then ran it to try to track a set point of our outlet temperature for our reactor.